So I call this question the Speedy object question, and again, a common related rates type of problem. Sometimes you'll see this problem or this strategy used to model particle movement. In this example, we're looking at how the movement of two cars at an intersection are connected to each other through their rates and their speeds. Okay, so let's read through the question and then we'll take you through how to calculate it. So in this case, we have a police cruiser. It's approaching a right-angled intersection from the north, and it's chasing a speeding car that has turned the corner and is now moving straight east. So here I've got my picture, and I just drew myself a little northeast, west, south, a little compass there. And I have from the north, I have my police cruiser coming in. It's at this point right here, and you can see that I have a car going towards the east. That would be this point right here. And when the cruiser is 0.6 miles north of the intersection, so because this is a vertical axis, it's north, I just chose to call it y. So I said that y is equal to 0.6 miles. So when the cruiser is 0.6 miles from the intersection, then the car is 0.8 miles east of the intersection. So because this is horizontal, I decided to call it x. So I have x is equal to 0.8. The police car has a radar, and the police determine with the radar that the distance between them and the car is increasing at 20 miles per hour. So you can imagine the police is sending its radar towards the car, and it's moving in this direction, it's moving in this direction, and the distance between them is increasing at a rate of 20 miles per hour. So if the cruiser is moving at a speed of 60 miles per hour towards the intersection, we want to know how fast is that car actually moving. So what's that instantaneous speed? Instantaneous measurement of the speed at that moment when it's moving, when it's 0.6 miles away and 0.8 miles away. So you'll see here with my direction, I said that moving north is positive and moving east is positive. So when I came up with my rate of change here, I know that my dy by dt, so the movement of my police car with respect to time is negative 60 miles per hour because it's going towards the south, whereas my dx by dt is what I'm trying to find. That's what I'm looking for, the speed of the car. I'm going to guess that it's going to be positive because I think I'm going towards the east, but we'll see how that all works out. And I know that I just said that d is the distance between the police car and the car, so that the side length is d, and that the change in d with respect to time is 20 miles per hour. So that's that information that's given right here, 20 miles per hour. So again, just kind of summarizing everything I know. I'm trying to find dx by dt, which is the speed of the car in miles per hour. I know that y is equal to 0.6 miles. I know that dy by dt is negative 60 miles per hour. I know that the change in the distance between the two cars with respect to time is 20 miles per hour. And I can actually find d as well, because I can see here that this creates a right-angled triangle with a side with two legs of 0.6 and 0.8. And when I throw that into the Pythagorean theorem, I get a distance between the two cars as being 1 mile at this particular point in time, so that the d is equal to 1 mile. So using all this information, I want to be able to connect this with a right angle or with an equation, and the equation I'm going to use here is a right-angled triangle Pythagorean theorem equation. So I know that a squared plus b squared equals c squared with this right-angled triangle formed, which means that x squared plus y squared equals d squared. So there's my formula, and what I'm going to do next is I'm going to take the derivative of my x squared plus y squared equals d squared with respect to t, so I can take d by dt of both sides, and that leaves me then with the derivative of x squared, which is 2x, with the dx by dt tagged on, and the derivative of y squared, 2y, with my dy by dt tagged on, equal to the derivative of d squared, which is 2d, times dd by dt. And because I'm looking for dx by dt, I just took that extra step of rearranging the equation. I brought this, I subtracted this from both sides, so I have it negative over here, and then I divided both sides by 2x here. So here's my equation for dx by dt, and finally, I'm going to take the values that I summarized up here, all of my given information. I'm going to plug it in. I know my d is equal to 1. My dd by dt is equal to 20. My y is equal to 0.6. My dy by dt is negative 60. And my x is 0.8. And when I calculate that, I end up getting dx by dt, or the speed of my car, as 10 miles per hour. And again, this is positive, as I would expect, because it's going towards the east, which I defined to be in the positive direction, which is perfect. So we can conclude then that the speed of the car is 10 miles per hour.